Right. Let's do some Leetcode. Maybe some monkey type. Maybe just one, just to warm up the fingers. Alright, Leetcode. I'm going to try and do... It's a good question. Might try another graph problem. Lone graph. Might be difficult. Should I try a backtracking though? Backtracking might be useful. Okay, I might try backtracking. Backtracking. Subsets. So given an array nums of unique integers, return all possible subsets of nums. The solution set must not contain duplicate subsets. You must return the solution in any order you may. So nums is 1, 2, 3. You return the empty list 1, 2, 3. 1, 3, 2, 3, 1, 2, 3. This is going to be an interesting one, yeah. I feel like you would use recursion here. You know, what are the subsets of this subset? But, you know, maybe, you know, this is something you append or you add to the result. Maybe. Yeah, there's some sort of way to do this. Let's go look at the solution. You can use depth first search. Really? Advanced algorithms, data structures, and... Okay, well, let me have a look at this. So result is empty, subset is empty. You do the DFS, and you start DFS from 0. If 0 is greater than equal to the length of the numbers, so the numbers being, say, 3, then you append the subset copy, and then you return. Otherwise, the subset append, you add the number, you go to the DFS subset pop, and you go to the DFS. That's something we need to see from an example.
Hey everyone, welcome back, and let's write some more neat code today. So today let's solve the problem subsets. So we are given an integer array nums, and all we need to do is return every single possible subset that we could create from the input nums. And we do not want to include any duplicate subsets. So what is a subset? Well, let's say we have 1, 2, 3 as our input. One subset, of course, would be 1, right, by itself. Another subset would be 2 by itself. We could do 1, 2 together. Now, what happens if we do 2, 1, right? We just swap the order. Does that count as a different subset, or is that the same as this subset? Well, they're the exact same. We don't care about the order. This is not a permutation. This is a subset. So it's not a permutation, it's a subset. So we do not want to include duplicates, and this counts as a duplicate. We're not going to include it. And 3 is another subset. 1, 3, 2, 3, 1, 2, 3. The original input is technically also a subset. And we also don't want to forget the empty subset. So no matter what we're given, an empty subset is technically a subset of this as well. So if we want to create all the subsets from this input, we have a choice for every single element. So for this 1, we have a choice of include the 1 in our subset or not include the 1, so we get an empty subset, right? So we have that choice, and we have that choice for every single input element. So in total, we have 2 choices here, 2 choices here, and 2 choices here. So this is going to be 8, or in other words, 2 to the power of n, where n is the size of our input. Right, so this is the number of subsets, and we don't want the number of subsets, we actually want the subsets themselves. So how long could a subset be, right? Well, we could have a subset 1, 2, 3, right, the size of our input. We could also have subsets that are smaller, right, like 1, 2, maybe 2, 3. So as you can tell, this is not going to be an efficient problem to solve. We have this many subsets, and each subset could be up to length n. So the worst case time complexity of this problem is going to be n times 2 to the n, regardless of how efficient we make it. Because given the constraints of this problem, we don't want the number of subsets, we want the subsets themselves. We have to make it inefficient. So with this in mind, we can just jump straight into backtracking, which is the brute force way of solving this problem, but it's also pretty much the most efficient way. So like I said, for each of these elements, we have a choice. So I'm going to draw the decision tree. So first we can choose to add 1 or not add 1, and that will give us 2 subsets, 1 subset with just 1 and 1 empty subset. So along this path, we can decide now, do we want to add 2 or not add 2? So we'll do make it in a brute force way of solving this problem, but it's also pretty much the most efficient way. So like I said, for each of these elements, we have a choice. So I'm going to draw the decision tree. So first we can choose to add 1 or not add 1, and that will give us 2 subsets, 1 subset with just 1 and 1 empty subset. So along this path, we can decide now, do we want to add 2 or not add 2? So with one decision, we will add 2, and the other decision, we won't add 2. So we'll get 1, 2 as 1 subset, and the other subset will just be 1 by itself. And we can actually repeat that on the right subtree for 2. So we can decide to add 2 to this empty subset, or we can decide to not add 2 to the empty subset, in which case we'll get a subset with 2 by itself, or we'll get the empty subset again, right? This is where we're just not adding anything. And lastly, we can decide whether we want to add this 3 or not. So if we add the 3 to this subset, we'll get 1, 2, 3. If we don't add the 3, then we will remain as 1, 2. And we can repeat that decision over here. And that's basically what I'm going to do now, right? Repeat that decision for every single one of our, like you can call them nodes or you can call them leaf nodes. That's just what we're doing. So if I add the 3 here, we'll have a 1, 3. If I do not add the 3 here, we'll have the 1 by itself. So you can kind of see these are 4 unique subsets, right? Now let's build the rest of the 4 from over here. So I have the choice Do I add 3 or do I not add 3 to this subset? If I do, I will get 2, 3. If I don't, I will have 2 by itself. And you can see these two subsets are different from the subsets over here. These are still unique. And lastly, we can choose to add 3 to the empty subset, or we can choose not to add 3 to the empty subset, in which case we'll get a single empty subset. Now you can see we keep multiplying by 2, right? So here we had 1, we multiply by 2, now we have 2 subsets over here, right? We go down again, we multiply by 2, now we have 4 subsets over here, right? Then we go down one more time, multiply by 2, we have 8 subsets, and they're all unique. This is our result. This is what we're building with this problem. This is backtracking. Now, if you want to know how to do this backtracking solution in code, let me show you right now. So let's do this with backtracking. So we're going
the backtracking. So that's backtracking. All right, let's see.
to have a result list, which we're going to add these subsets to. And I'm going to do this with backtracking depth first search. And I'm going to write this function inside of this function so that we don't have to pass in this variable or this variable into it. We'll just have access to it by default. But I'm going to pass in I, which is the index of the value that we are making the decision on. So, you know, we had 1, 2, 3. So initially I'm going to pass in index 0 for this one. And you know, this will be index 1, this will be index 2. That's going to tell us whether we decide to add 3 or not add 3. So this I will tell us which element we're currently visiting. And so we know that the base case for this will be if I happens to be out of bounds. So if it's greater than or equal to the length of our input, we know we're out of bounds. And in that case, we can just return. Now, what like data structure am I going to use to build each subset? I'm going to have an array and I'm going to allocate it outside of the function so that we have global access to it inside of this function, right? So let's say let's actually call it subset. Let's say that it has the subset that we currently have. If we ever reach the base case, we know we've gotten past our leaf node. So what we can do is add that to our result. And I'm also going to add a copy of the subset because the way it works in Python and in most languages, this subset is going to be modified, right? So we know we have two decisions. So this is the decision to include nums of I. So this is like our left decision that I showed you in the picture, right? So what I'm going to do is to the subset, I'm going to append nums of I. And then I'm going to recursively run depth first search on the next element, so I plus 1. So this is going to be like the left branch of our decision tree, and this is going to be the decision not to include nums of I. So basically we're skipping nums of I. So how am I going to do that? I'm going to take the subset and just pop the element that we just appended. And then I'm going to recursively run depth first search. I'm basically going to do the same thing. So these two function calls, while they look the exact same, they're going to behave slightly differently because for this recursive call, it's going to have a different subset given to it. And this recursive call is going to have an empty subset given to it. So now the only thing left for us to do is call our function. Of course, we're going to pass an index 0. That's the first value. And then we can return our result. So as you can see, it is an efficient solution. Luckily for us, the order that we have our subsets in the result doesn't matter. So for example, if we had an empty subset and we had 1, that's the same as if we returned 1 and the empty subset, right? Like the order that we put the subsets in doesn't actually matter. But again, I hope this was helpful. If you enjoyed, please like and...
So I'm going to try it my way because his way is still a little bit unconventional, so to speak. So we'll see. All right, so we have a result, return the result. BFS, I could do it in BFS or DFS. I'll do it in BFS because that's how he's done it in the question. Right, so there is some sort of BFS going on, right? And we're going to have BFS here, but he's used a subset function. And this BFS has to keep track of that subset function. Thing is, this BFS, I could build out the boilerplate here. Q equals collections.dequeue. But there's got to be something in that while Q. And then you got to consider the left and rights. But what goes in here? At each node, you keep track of your current subset and your current subset. Am I convinced? Yeah. So have some subset. Start off with some subset, empty subset. Add that empty subset to the queue, and then subset is equal to q.pop left. Is it pop left? Yeah. That subset. Give me a sec. Yeah. We have to add that value to the result. And then you have to also consider nums. So I think that's what I'm missing. An I. If I is greater than len of nums, I would say greater than or equal to. Then you would add nothing to the breadth first search. So if it is less than learner nums. Q.append sub and I plus 1 sub what do you add? You add nothing or you add something. So you would add nums I and you would also add just sub I. What would you return? The result? Okay, well, I'm just doing a function in a function. Subset, why would I need that anymore? When I can just define it like there's going to be something wrong with this. Invalid syntax. Subset is empty. How is this invalid syntax, to be honest? Let's print the sub and see what that looks like. Perhaps you can't do it. Yeah, so I just doesn't exist here. I'm gonna say index of 0. Non-type object has no attribute append. So first it was nothing. It becomes a non-type object because possibly it gets just doesn't exist anymore. So maybe perhaps this is why you need the copy. Okay. New, maybe I'll just call a new sub. We'll have to see. New sub is none. How? Subset is empty. New sub is I feel like it has to be. Let me try and copy this. What if I just did a sub.copy? Nums I just remember that. Oh right, this isn't a I forget, right, that this isn't this yeah. If I do that and return new sub. Alright, so I have to make this a list. Yep. So that means I can, remove this and just go like that. And then I just need to say you only append if. If what exactly? If it doesn't already exist in the list of results. I mean, you could just make a set, I suppose, and return the set. This is going to be returned as a set though. Unhashable type list. Ah, man. Also, that's the other thing. You'd have to convert it to... Yeah, I don't like to convert things. I'd rather have something efficiently doable. But if it was a set, you can just convert it to a tuple and then you would have to convert it all back out into a list. That's a possibility. Okay, well, let's try that possibility in the offset. Oh, in the off chance that that also is a valid solution. Okay. Yeah, your output was, but we expected a list of ints. So, I'd have to make a conversion back like list res. I know this isn't even going to be right because the set in it is not. Right, so I need to have a list R for R in res, and then make this a list. And then that would work. But I don't like that solution. I don't want to use a set here. Except, is there any other way? You'd probably have to. Because if you have just a list, you can't keep track of what type of values you've visited. Unless you made it a set of some sort. Or perhaps you made it a hash table. If you did make it a hash table, it'd still be a value of 1 or 0, which would effectively make it a set. So it's a matter of picking your poison. But there you go, so that would solve that. Yeah. So Hoo boss, I mean, if you're still here, yeah, you're right. Native, try Candace. I don't know what Candace is. I don't think this is... do you also do the recursive solution? I usually like to just keep it in queue. So I guess sometimes I'd only use the recursive for DFS stuff. So I usually just do normal while loops. But I do know how to do it in DFS. Like I looked at the solution. I just always find it better to have a while loop, just because I can change this to a DFS pretty straightforwardly every time if I wanted to. So that would be a DFS solution, and that would still work. But I'll just keep it as a BFS. Okay, regardless, control, we're going to copy all this. And just paste it into Leetcode. It's probably going to be less efficient than all of the solutions on this platform, I reckon. Yeah. Just because, you know, there's an extra level of computation required. using a set would make it a I would have to make it an O of n. And even with the dq, that's still O of n. So I think we're fine. Okay. Also going to add it to my Leetcode repository. And it's named what? 78 subsets. Okay, so that question's good. Backtracking seems okay, like, I'm not too mad about it. You know, there's also two-pointer problems as well that I want to revisit, or sliding window. You know, if I do sliding window, it's pretty much a two-pointer problem. And, you know, linked lists are actually something I'm also concerned about. But, you know, maybe, yeah, one of these, is what I need to do. Permutation in string. Okay, let's try the permutation in string just quickly. We'll try and think through it. So you're given a string s1 and s2. Return true if s2 contains a permutation of s1, or false otherwise. This means that if a permutation of s1 exists as a substring of s2, then you return true. Both strings only contain lowercase letters. All good. So you have ABC, LECABEE. It's going to be true because if S2 contains a permutation of S1. Yeah. So ABC, CAB. Then you return true. The substring CAB is a permutation of ABC and is present in LECABEE. Okay, and example 2 is ABC. LECAABEE, and that's not possible. Yeah, so you're going to use some sort of set here. You're going to use some sort of sliding window. You're going to use yeah, a combination of both. So let's say you know ABC is going to be, S1 is going to be a specific unique set. Instead of a set, it is actually going to be a hash table, because you can have any number of letters of any kind. So you have duplicates, which means you have to keep track of the numbers. So a hash set would likely be what you use. With LECABEE, you would increment your right pointer if you would increment your left and right pointers if L is not in the set, in the hash map that you originally found for S1. And at E, you would do the same thing. At C, you would increment the right pointer only and see that A is also in the hash map, and you increment it again, increment R again. And then you would see B is in the hash map again. You would decrement the hash map. Do a check on the hash map, perhaps. That's still going to be like a non-constant operation, unless you also keep track of how many, in the hash table, in the hash set, you also keep track of a variable to see how many in the hash table you have taken out. And if that number is equal to the length of the S1, then you know to end the execution there and just return true. And you wouldn't need to go any further than that. I think that's how this problem was solved last time when I did this question. So let's have a attempt. And we're gonna have S1 hash table, which is equal to default, say collections.default dict int. We're gonna say for S in S1, S1 ht S plus equals to 1. And then you would say, well, you have that set now, you would probably have to keep track of now a variable length, matched length or something, or just matched, just call it matched, but it's starting from 0. And then you would say left and right pointer is equal to 0 and 0, while r is less than, wait, do I need r is less than, or do I need something else? You would return false if you can't find anything, or you would return true if you do find something. Okay. So if you do find something, if you reach the right side, the end of the right side, so what would happen if you do that? So if that B was at the end, you have CAB. If B was at the end, you would still need to say that that's good. But say, you know, the end was just after the E, perhaps. What would you do? You would not continue, right? If the R was at the end, you know it's never going to work out, right? If the R was at the end of B, you know you've scanned as much as you need to. So while R is less than the length of S2, we got to somehow return true if some condition occurs. Now, if what condition? You return true if the number of matched is equal to the len of the number of matched is equal to the len of S1. Or I should say the max matched. I could have the max matched. I could have the max matched. There are ways to do this, many. So regardless, somehow get matched now, the number of matches. If L, so if something, right, there's going to be a situation where L and R, L is equal to R, R is equal to R plus 1, if R, if S2 are not in S1 hash table, and you would have to reset I'm going to write a current S1 hash table is equal to S1 hash table dot copy. Actually, I'm not sure if that's allowed. Dot copy on a hash table. Okay, so you can do that. Then you would reset. Else it is in that maybe check, if ht is now s2 r is equal to 0, you delete car s1 ht s2 r. Anything else? So it is in that your matched gets incremented your matched gets incremented, sure. Should equal to 0 again. R is equal to R plus 1. And if matched is ever equal to the length, then you would return true. So that worked for the two test cases we had, but for these, so ADC, DCDA, okay, right, because if I went from ADC, D is in it, C is in it, D is not. So you would have to increment L only by 1, not by R. Because otherwise you're just skipping potential matches. I think that's right. Wait. Then R has to equal to L. Right? Because you have to start from this again. Let's go. Hey, that was pretty good. Pretty good. You know? Arguably, that's even less code than what we have here. Not bad. Not bad. Okay, oh. The other day I also learned about what you do here as well as a potential alternative to using a hash table. You know. Oh, but except that's only... No, yeah, you can keep count like this. You can keep a count like this. This is definitely something I gotta remember to use more often. Because, you know, I can, but I don't. Definitely I could use this instead of having a hash table of a count. Instead of a hash table of a count, you can use this. Okay. Well, that's a solution. Solved.
Hey everyone, welcome back, and let's write some more neat code today. So today let's solve the problem permutation in a string. And there's actually two solutions to this problem. One is the 26 times n solution, and there's another solution that's actually just big O of n. Now we know that a constant number here doesn't actually affect the overall time complexity, but that being said, I'm still going to focus on the slightly more optimal solution. Because it's a little bit more difficult, but it's also interesting, and it's a pattern that's actually used in other Leetcode problems as well. So we're given two strings, s1 and s2, and all we want to do is return true if the string s2 contains a permutation of s1, and we return false if that's not the case. Now, you can get bogged down and really confused with the explanation of this problem, like focusing a ton on permutations, but I'm going to try to simplify this for you immediately without going down too many rabbit holes. And let's actually take a look at this first example. So we see that S1 is the target string. That's what we're trying to look for. We're looking for a permutation of this string somewhere inside of S2. Can we find it? Now, what does permutation mean? Well, we could actually, create a permutation of this string, which would be really complex and annoying. But we see that over here, there actually is a substring of S2, and it's a permutation that matches S1. It's
Love to see that. I solved the solution in almost the least amount of time. Which, to be fair, I am not mad about.
BA, right? The exact
I'm just
same
happy to have solved
characters,
it.
just in a different order, which is perfectly fine. Now, by the way, AB itself technically counts as a permutation of itself. So this string is also allowed, but since you kind of see, what we're really just looking for is there a substring of the exact same size? So this is 2 characters, so we have to look for a substring of 2 characters here, right? We can't just take 3 characters and say that that's the permutation. But, you know, we're looking for a window same size as this, and it has to contain the exact same characters as S1, just maybe in a different order. Now, does that kind of sound familiar to you? Well, it's the same thing as looking for an anagram, right? We're just looking for the exact same characters. We don't care about what order they're in, right? So it's looking for an anagram, so we can actually use a typical sliding window technique. We're going to look at every window in S2 that's the exact same size as S1. So in this case, length 2. So we're going to look at the first 2 characters, then the next 2 characters, then the next 2, etc., until we find an exact match with S1. Now, if we were actually comparing the exact characters, that would be pretty annoying. The time complexity in that case would, let's say, be n times m, where n is the size of S2, m is the size of S1, because we're looking at every single window. But we can do it a little bit better. We can reduce it to be 26 times n if we use a hash map, because actually in this problem it's written all the way at the bottom of the description, so it's not on screen, but they tell us that all the characters in both of the strings are going to be limited to lowercase a through lowercase z, so therefore the size of our hash map is going to be at most size 26. There's only 26 characters, so as we build that hash map, we're actually going to have 2 hash maps. We're going to have one hash map for S1, which is going to stay the exact same. We're also going to have a second hash map for S2, which is going to have the characters of the current window that we're at. So every time we create a window, right, each time we shift our window to the right, we're only just adding one character and maybe removing the character that was on the left. And then once we have those 2 hash maps, we're going to compare them if they are equal, which is a 26 operation, right? There's only 26 characters, and so that's where we get this time complexity from. But there actually is a better way. This solution is doable, it's easy to code up, and you can do so if you would like, but I'm going to show you the slightly more optimal solution, which is actually not even going to have this 26. It's just going to be big O of n. So let's look at the big O of n solution. And it's actually similar to the previous solution we discussed. We're actually going to still have 2 hash maps, one for S1. So as you can see, we counted the occurrences of each character. We call it S1 count. So we have 1A, we have 1B, and 1C. So we've filled our hash map with the same values. And our S2 hash map is empty because first we're going to set our window here, and then we're going to continue to shift it by 1 each time. But the difference here is we're not actually going to be comparing the 2 hash maps together. We won't need to, because we're going to keep track of one more variable. We're going to call it matches. We're basically going to have a little shortcut. Initially, this is going to be set to 0. I'll just create a box for it, even though it's just going to be a single value, but we might be updating it to other values. But this matches variable is basically going to be a shortcut that's going to allow us to not have to compare the entire hash maps each time, which we know in the worst case could be a 26 operation, having to look through every single character of the hash maps. Because this matches variable is actually going to maintain the total number of equal characters in each of these hash maps. And actually, even though I didn't draw the entire map for S1 and S2 in this case, because actually we know that there's A through Z, there's 26 characters, and I didn't actually draw out the entire thing, but we are going to fill in the values in the code, because we know that the rest of the characters in S1 are going to be of count 0, right? And matches is going to tell us the exact number of matches of each character between the 2 hash maps. So we want to know, does the A count of S1 and of S2 match? If it does match, then that's a +1. If it doesn't match, then that's not a +1, right? And we want to know the number of matches for every single character, and we want to know that initially. right? It could be 26 matches or it could be 0 matches, right? It could be any value in between. But once we have 26 matches, that means that for some window in S2, and by looking at it, we know that this is going to be the window. We know that this window has 26 matches with this window because they both have a single A character, a single B character, a single C character, and for the other remaining 23 characters, they both have 0 of those characters, so therefore they have 26 matches. That's what we care about, and we can do that with a single variable without having to look through the entire hash map. Let me show you the algorithm to do that. It's pretty straightforward, actually. So first thing we're going to do is actually just look at the first 3 characters of S2 and then fill up our hash map. So we have a single B, we have a single A, and we have a single X. Now you can see that this is what our hash maps actually look like. We have looked at the first 3 characters, and now what we're actually going to do, for the only time, we are actually going to iterate through both of these hash maps comparing each character. We actually do have to do that at least one time, but it's a single 26 operation. And then after that, we'll only have to just iterate through this string. So the overall time complexity is going to be n plus 26, which we know is going to be equal to big O of n. It's definitely better than if we were just doing 26 times n. Okay, so we're going to look at every character. A, they both have one A, they both have one B. S1 has a single C, but S2 does not have any C's, so therefore they have 2 matches, A and B, but C is not a match. Then we're going to look at all the other characters after C, and we're actually going to see that yes, there is a match, right? Because they both have 0 D's, they both have 0 E's, they have 0 F's, etc., etc. But then we're going to get to X. Okay, this has a single X, but S1 does not have any X's. That's not a match, but they both have 0 Y's and 0 Z's. So all in all, they actually matched every single character except for C and except for X. Those were the only characters they didn't match. So actually, initially we have 24 matches. Next, we're going to take our window, which was like this, and we're going to shift it to the right by 1. When we shift it, we're obviously removing a character from the S2 window. We're removing a B. Now, as we make changes to the count, we want to know, does it affect the number of matches? So here we have 1, right, which was equal to what it was supposed to be in S1 as well, but now we're changing it to a 0, so therefore it's not matching with what it previously was matching with. Therefore our matches total is actually going to be updated down.
Okay, I mean, I understand all this. I've seen it before. Alright, I'm done. That's it for that Leetcode stuff. So however, you know, the question also lies whether I should prepare for some more system design. You know, the thing that is stuck for me on the system design, what am I worried about in the system design? I don't know. I don't know if I should be worried of anything, because I feel kind of okay. And I don't want to overthink things too much as well. I just want to do it. And just speak to the interviewer, you know, just like have good conversations with the interviewer. Discussing these types of problems. And yeah, I don't think I know anything else to say. Okay. I think what I'll do now is just some silent study. I'm going to do silent study on a lecture because I've been procrastinating that, so to speak. You know, there's a lecture that I got to catch up on all the way from last week that I gotta really do. And then hopefully by then it'll be lunchtime, and by lunchtime I'll have a shower. You know, maybe I'll be able to go to the gym, And then the presentation slides are, yeah, man. Don't know how well I'll be able to do those, but you know, I need to do those well. I need to do those well. I'll do as much as I can. Okay, but this lecture is current priority to do and watch. And that's what I'm going to do right now. Okay. All right, silently. Here we go. I'll just have a quick minute, 2-minute break.
Okay. So, those who are online, can you hear? So, hello. Those who are online, today there won't be any guest lecture, but we will continue with polynomial rings. Okay.
Alan says, I remember struggling to understand backtracking. Yeah. After searching online, it makes sense now. If I were to explain it though, you know, like, you just think of backtracking as building your own tree, satisfying constraints, and you would abandon a node in the tree once the constraint isn't satisfied anymore. But, you know, part of, I guess, all Leetcode questions, you know, it could be under a section of backtracking, but, you know, it never encapsulates the whole concept of backtracking. Yeah, I like to think of it as a decision tree. Yeah, exactly. So I agree with that. I think, you know, backtracking doesn't work like you think it should until you see a proper example of it working the way it should. And the problem is Leetcode questions don't always give you a fully backtracking problem where it's like all the features of backtracking or something. Anyway. You got a rejection email today? It hurt so bad when you thought you did well, yeah. Unlucky, man. I mean, ruined your... Man. It's alright, I know how you feel. I've felt the same before. You know, for example, like I got like an Atlassian interview. Like I got to the third interview, which was the final interview, and I didn't pass it. And it was a behavioral. So my behavior wasn't good enough. Now I've learned a lot from it. This is like 5 months since. So you'll be fine. Although I still have nightmares sometimes about it. AWS, damn. Unlucky. I mean, good riddance. Don't even think about it. I mean, yeah, you should think about it. At least know what to improve on. But yeah, no, that kind of sucks. I know how you feel. We're equals in that respect. Yes, it is Obsidian. You tried using Obsidian, but you like the convenience of Notion? Yeah. I would agree Notion is pretty convenient, but yet again, the privacy policy, man. I just can't handle it. It's too much for me. And everything's fed into their AI tool that just makes it a little more alarming to me. So I haven't used Notion since their AI was released. But also I've just found peace with Obsidian in all its quirks and issues that it does have. For example, like there's a self-hosted live sync that I use, and there's lots of bugs with using that, like, you know, compared to the Obsidian sync functionality. You self-host it, but self-hosting it also has its own issues, and that's the issues that I face 24/7. But yeah, I've lived peacefully with it. Okay. Anyway. Oh, you don't have any personal stuff on it though, just notes, yeah. I mean, that's fair. I guess the other thing is, like, I've also liked using Obsidian because of this Excalibur extension that someone else on stream also recommended me. So, you know, I've been using this ever since that, and I've actually found it pretty good to learn stuff on, rather than just like typing notes out. You know, you can always create notes that are more concise when you're not constrained by text, so to speak. You know, you can have like your own mind maps. That's what I like about it, especially. Anyway, I've also just embraced imperfection, and I think that's to my benefit. Not saying that you're embracing imperfection, you're embracing perfection or anything. I'm not saying any of that. I'm just saying personally. Anyway. Yeah, gives you NVim plugins PTSD. Okay. Yeah, no, I see. I know what you mean. Yeah. I messed around with NVim for a bit as well, but my PTSD of configuration comes from like Android. I actually used Android a lot back in the day in high school, and then I was like actually just obsessed to the point, like, this is high school, right? So I kind of like just wasted time 24/7. But still, back then, if I were to touch a phone, I'm like, damn, how could I just improve the look of it? And I'd improved the look of it for so long. That was my configuration dilemma back then. So from that, I've learned to not worry too much about NVim, so I'm lucky in that respect, or even Obsidian extensions. So And I decided to buy an iPhone. Yeah, right? So like, you spend more time configuring Vim than actually using it to code. That's what I was, but with my phone back in high school. You know, I'd be like, how could I improve it so much that as soon as I open my phone to try and text someone, I'm like, okay, wait, this looks kind of bad. Let me do it. Let me try and think of a better way to do it. It's almost like the nail, like you see a nail everywhere after you do something. I forgot the exact phrase people use. You really like this new IDE called Zed. I use Vim Motions now. Yeah, okay, nice. I mean, I've heard of Zed. I've heard positive things. Never used, but I'm sure it's more lightweight than VS Code for sure. I probably need it for this laptop, which is only running 8 gigabytes of RAM. Literally the baseline of the baseline for a Mac. Okay, but it still works. It can still stream for me. And I can still study on it as good as I am now. Okay, regardless. I'm gonna focus. Alright. Polynomial rings and finite field. We have learned the properties of numbers mod n that are sufficient to understand many modern and classical cryptographic primitives. When n is a prime number, the structure naturally gives rise to a field also known as non-zero numbers less than the modulus. Prime are all invertible. What the heck? What the frick? When n is a prime number, the structure naturally gives rise to a field as all non-zero numbers less than the modulus are all invertible. Oh, yeah. So that's because of the phi function, Euler's function, Euler's theorem. Yeah, we established that like week 2. We have also learned that when n is a power of prime. Okay, hold on. Remember? So it's invertible by multiplication to get some value equal to 1. But we have found that the greatest common divisor... Right. Is it the greatest common divisor is equal to 1? Let me recall. So the greatest common divisor of the prime and the number... prime and the field... Prime and a number in the field is equal to 1, right? Because that makes sense. This is why we're talking about invertibility. This is why every number has its own invertible counterpart in the field. Okay? Yeah, makes sense. Okay. We have also learned that n is a power of prime number. We also have learned that when n is a power of prime number, n is a power of the prime number, then there are zero divisors, and phi n is always less than n, which makes it not so ideal to define multiplicative structures for cryptography. What does that mean? So we have also learned that when n is a power of a prime number, n is a power of a prime number, so say q, a, or a to the power of n, mod q maybe. Then there are zero divisors. And phi n is always less than n, which makes it not so ideal to define multiplicative structures for cryptography. So phi n is always less than n as a fact. Where n is a power of prime number, then there is a zero divisors. N is a power of the prime number. Then there are zero divisors. And phi n is always less than n, which makes it not so ideal to define multiplicative structures for cryptography. Right. So I gotta underline these because whoops. So does there exist a field of size which is a power of a prime number? We will answer this question with the introduction of polynomials as field elements. Alright, polynomial rings and finite fields. So recap the group, ring, and field. So the group, the ring, and the field. So let us visit a few concepts that we have learned already. A group is a set G together with a binary operation dot on G such that the following three operations hold. So dot is associative. There is an identity element E such that for all A in an element of G it equals to A. And for all A in an element of G, there exists an inverse element, A to the inverse, such that it equals to E. If the group also satisfies AB is equal to BA, then the group is called abelian or commutative. So this is what it means to be a group. So this is what it means to be a group. And normal numbers are just an example of groups. Like the natural numbers, for example, is an example of groups. Oh, is it? No, it's just the real numbers. Real numbers is an example of groups. Is it? Actually, you know, there's always like little cases. Okay, a ring R plus and dot is a set R together with two binary operations, not one, but two, where you have addition and multiplication such that R is an abelian group with respect to the addition. Dot is an associative, that is ABC and ABC for all of them, and the distributive laws hold, that is for ABC we have a this and this and this. So ring and group, okay, so sure, right? And then field. We note that the set ZP, P minus 1 where P is prime, satisfies axiom of a field, where the set is closed under addition. and that's agreed upon. Since P is a prime number, any non-zero element in ZP has an inverse. Yep, I agree. And you can verify that additions and multiplications are distributive. So in ZP, unlike integers, P times an element in the field is 0. P times any element in the field is 0. Correct. This leads to a concept called characteristic of a field. We also denote Z star P as a set of non-zero elements of ZP. A set of non-zero elements of ZP. I thought that would include a zero element of just the empty set. But apparently it does not. So I should highlight this then. Characteristic of F. Question is, question is, shall I go to the gym today? I think I will, but I think I might do it after lunch. I think the stream will also be shorter slightly because in the afternoon I'm pretty sure I'm going to be pretty honed in on other stuff to try and finish off. And I don't think there's really much adequate time to be streaming at the moment, but okay, regardless. Look, as soon as I start this lecture, it's gonna breeze through these 3 sections like it's nothing.
First operate and then operate with A is same as first you operate with A and B and then operate with C. That shows that the operator is associative. That you can put the bracket wherever you want, if there is a consecutive set of operations. So there is an identity element for every element. So there exists an identity element in a group such that for all A, some element belong to group, A times identity is same as identity times A, and it gives you the A. Identity is such an element when you multiply it or when you operate it with another element, gives you the same element. Then you can also have an inverse element, another element called A inverse, symbol with this, I think you're already familiar with it, where you operate with A with its inverse, you always get identity. Then also, if the group also satisfies that A operated with B is same as B operated A, then we call it as a commutative group, or also sometimes known as abelian. So this is named after a famous mathematician, Abel.
Abel.
Okay. So, okay. I will remove this. Okay. So next you do similarly. Now a ring, another structure ring, is set with 2 operations. One is called addition So the binary operations are, one is called addition, other is called multiplication. So how you define ring as, take that element, it's a set of elements again. With respect to addition, it's a group. That means all the elements are closed under group. And with respect to multiplication, it is associative. And also it holds the distributive laws. For example, you have a plus b plus c times a is same as a times b plus b times c. See how you obtain bracket and do that distributive law holds. Such a thing is called ring. Now we note that ZP is a polynomial ring addition, right? Then we introduce an idea called characteristics. I think I introduced this idea before, characteristics. Are you clear about characteristics of
No.
the finite field?
No.
Yeah. Now what I mean by a characteristic is,
Yeah, so let F be a field with a multiplicative identity 1 and the additive identity 0. The characteristic of F, sometimes written as char F, is the smallest integer n which is greater than equal to 0, such that the addition of the 1 with itself times what? With the addition of the 1 with itself, n times results in 0. Note that for real and complex fields, you cannot find a positive integer n satisfying the above criteria. In contrast, the residue class rings Zn, the characteristic is n. When n is prime, Zn is a field. So this is a little bright actually to my eyes. So in contrast, the residue class rings Zn, the characteristic is n. When n is prime, Zn is a field, and accordingly the characteristic of Zp is p. One of the consequences of the above property is that equals to 0 is the field for any alpha. Zp is the main source of prime fields. However, for algebra, we know that the finite fields of the size of prime powers exist. How do you construct them? I'm shaking my head, man. They really make this stuff like for the mathematically inclined. You know, like, god damn. No complaints, but note that for the real and complex fields, you cannot find a positive integer n satisfying the above criteria. Hence, the characteristic of the real and complex fields is 0. Oh yeah, so if it's 0, then, 0, addition of 1 with 0 is 0. So the characteristic in the real is 0. In contrast, for residue class rings, the characteristic is n, where n is prime. Zp is a field, and accordingly, the characteristic of Zp is p. Makes sense? One of the consequences of this above property is that p equals to 0 in the field for any alpha. Zp is the main source of prime fields. However, from algebra, we know the finite fields of the size of prime powers exists. How do you construct them? Polynomial rings over the field in an expression. All right, let's see.
Say you have a ZP, okay? Z for modulo 5. Let's say Z5. Take one element, like number element 1. You add 1 plus 1, 2 plus 1, 3 plus 1, 4 plus 1, 5. 5 becomes 0. Right? So this is a special feature of finite field where you take one element and you add a certain number of times, then it becomes 1. It becomes 0, which is additive identity. That clear? Huh? So this is just an idea, because what you have to think is the possibility. For example, you take Z3. What is the characteristics of Z3? Z3, how can it be 1? Because 1 is not 0, right? You add 1 3 times, it becomes 0. Hence, 3 is the characteristics of Z3. What is the characteristic of Z5? 5. What is the characteristics of Z7? 7. So this is very easy. We can understand. But the interesting point is that even if I consider polynomials over this ring, let us say Z3, okay? And you take polynomial, means x is an element in the polynomials, right? Now you take even x 5 times, it will become 0. You see the point?
No.
So even though sometimes the size of the alphabet we are considering is greater than p, for example, take polynomials, but characteristics is still the same. You see the point? So if I take even the polynomials, the characteristics is same. Correct? Is that clear? Is there any problem with the definitions here? Okay, good. No issues. I can progress to the next. Yeah. I think you're still thinking. What is the question that is bothering? Hello. Yeah, but what is that you're still thinking, right? That means, is there any gap? Whatever I said, and any question?
Man, I should have been in this class.
Hello.
Like,
Yeah. Now, characteristics is the property, right? Property of the, let's say ZP. Characteristics is ZP means by adding P, by adding one number, let's say 1 unit, P times, it becomes 0. Which is not the case with real fields, for example. In real fields, you have a real number. You take any non-zero element. How many times you add, you can keep on adding, it will become bigger and bigger only. It will now become 0. In real numbers, yeah? Clear? So, but this is a different thing. Our departure from real fields, this finite fields, you have, when you add sometimes finite elements of non-zero element, you get 0. So we are recognizing this property. That's all I am asking. You recognize this, yeah? It's a property of the alphabets that we are working on. Correct?
okay.
Yeah, everybody clear now? So
Yeah,
that's
somewhat.
what I said. When n is prime, ZP is according to characteristics is P. So one of the consequences of work property is that P equal to 0. So P in ZP, P is 0, correct? Z5, 5 is 0. Because if you divide by 5, the remainder is 0. So that's all I'm asking. So because this is the one which is conceptually many people will have a problem. Okay. So any field element you take, ZP, even let us say when you take Z5, the situation with the 3 is also same. Let's take a number 3. I add 3 5 times, it will become 0. 3 plus 3, 6, plus 3, the 6 is already 1, then 1 plus 3 is 4, 4 plus 3 is 7, it's 2, 2 plus 3 is 5, 0. So 5 times you add even 3, it becomes 0. You add 8, 3 is also same. Let's take a number 3. I add 3 5 times, it will become 0. 3 plus 3, 6, plus 3, the 6 is already 1, then 1 plus 3 is 4, 4 plus 3 is 7, it's 2, 2 plus 3 is 5, 0. So 5 times you add even 3, it becomes 0. You add any non-zero element in finite field Z5, 5 times you add the same number, it will become 0. Because when you're adding 5, a particular number means what? It is p times a number. But p is already 0, 0 is always 0, correct? Is that clear? Sometimes, there may be some, if you all get some confusions or some ideas, don't doubt about it, just tell. That's very important.
Sure.
Okay, good question. I can go to many thanks. So I'm taking, let us say, Z5. Okay?
I don't know why I'm pointing.
Z5. Now what are the elements of Z5? 0,
1, 2, 3, 4.
3, 4. 5 is 0. 6 is 1 like that. That's the structure, right? Now I showed you the characteristics of Z5
It's 5.
So that means, let us say I add 2 5 times, and because it is associative, you can add this, and 2, that is 4 is another number, plus 2 is another number 2, like that. Let's say 4 plus 2 is 1,
Yep.
plus 2 plus 2. This is 3,
Yep.
plus 2, that is 5, which is 0.
Yeah.
I'm doing every day, the operations in Z5 is always modulo 5, right? So I could have just said, this is same as 5, this is
2 to
same
the power
as
5.
5 times 2 mod 5. Because 5 is there, this will become 0.
Oh, right.
Okay?
Fuck me, man.
So whether I add, see, as a group operation, you add these 2, you get one group, one element. Then then that element is 4. Then 4 times 2 is another element. So adding this in this abstract group, see, adding here is equivalent to adding in integers, taking modulo and keeping the remainder. Yeah, that's the definition of this field. But as a group, I can write Z5 plus 0, 1, 2, 3, 4, 0, 1, 2, 3, 4. 0 is, you get the same thing. You get adding the same thing. 1 plus 1 is 2, 2 plus 1 is 3, 3 plus 1 is 4, 4 plus 1 is 5 is 0. Yeah. So you can see that you can prepare this group table and add like this. Still the answer will be same. Okay? And that's what I said. The characteristics of a field is in a finite field, and we proved it with the Fermat's theorem that any type x power p is x mod p. Correct?
True Fermat's theorem.
You go with x, you get back the x. x power p minus 1 is 1 mod p, Fermat's theorem. X power p equal to x is Fermat's little theorem. Yeah?
Right, yep.
Correct?
Yep, I remember that.
We have already seen this behavior. So
Agreed.
this is actually in the multiplication part. Here I said the additive part. But in any case, characteristics comes into field operations again and again. Okay? Oh, good. So what I said was, because you are now adding p times, you get back the same element. That's the multiplicatively. In additively, p times x is 0. Okay? So this implies characteristics of a number. So whereas, of course, this is a multiplicative property. This is not immediately relevant to characteristics, but same idea, that because of the characteristics is helping here to get me this result. So we proved this x power p minus 1, but if this x had to be not equal to 0 in the group, or when we had the Fermat's theorem, I put x is to be relatively prime to p, which means that out of all these x elements except 0, all other elements are relatively prime to p. Okay, so that's why this is true only for x not equal to 0, but this is true for all x in the field. X power p equal to x.
It's true for all x in the field.
So these are the properties of that thing. What I am saying now next is very important. Even if I consider zp and let's take polynomial x, that means let us say example is z5 of x. 1 plus x is a polynomial, or let us say 3 plus x is a polynomial. Yeah? Clear? So now I'm just, how many polynomials are there here? How many polynomials are there in this? Infinite. Because you see, you can say you have z5, and let us say moment I put x and request find polynomial properties, addition thing, x plus x, 2x is there, x plus x, 3x is there, x plus 3x plus x, 4x is there, x plus 4x plus x, 5x, but that is 0 is anyway, 5x is 0, right? And then once you have 1 is there, 1 plus x is there, 1 plus 2x is there, 1 plus 3x is there, 1 plus 4x is there, 5 times 1 plus x is 0. So even what I'm saying is, you want to take a polynomial 1 plus x is a polynomial, and add 5 times, that this is addition in the group, okay? Add 5 times. I mean, just to make it, thing is, I'm putting that thing is not the operation just to say 1, 2, 3, 4, 5. 5 times I add in the group. Now this is actually 5 times 1 plus x actually, yeah, that is 0. So even if you have a polynomials over it, you get 0, correct? That is the consequence of characteristics of a field. So if you have a ground field has a characteristics p, then all polynomials over them also has a characteristics p. This is an important thing to be realized, correct? Clear?
I'm gonna stand.
You can put 1 plus 5x as well, but that is same as 1, because 5x is 0 and you get 1, right? 1 plus 5x is 1. But I just wanted to show you that 5 times 1 plus x is 0, which is done by this operations. Okay?
Nah, his explanation is not good. I can get it, but it's still just like scattered. I'd rather learn this myself.
So now let's go back to the lecture. Clear? So now what I'm a polynomial formally is an expression of the form.
Okay.
The polynomial in x is of degree n is given by that polynomial. Okay. I can now define a polynomial is an expression of the type f of x equal to f1 x power n up to f0, where the symbol x is an indeterminate and the coefficients fi are the elements of the field. The zero polynomial is f of
Hold
x0.
up. Bro, again, this guy. Look, he doesn't even elaborate like what these terms mean. Indeterminate. And the coefficients, this one and this one, are elements of the field. But why is it not equal to n? Man, this guy cooked, man. Absolutely cooked. This is what I imagine like most mathematicians to act and be. Regardless, I'm not mad. The zero polynomial is f x equals 0. The degree of a polynomial denoted is the largest index of a non-zero coefficient. Yep. Is 3. Is 0. The degree of a non-zero polynomial is always finite. By convention, the degree of the zero polynomial is negative infinity. Interesting. Yeah, okay, interesting. That's definitely not normal. Alright, sure. I'm convinced.
The degree of the polynomial is denoted by degree of f(x) is the largest index of the non-zero coefficient. So you see that 1 plus 2 plus 1 plus x plus 2x cubed. What is the degree?
3.
Similarly, you have a degree of 1 is a degree of x power 0, which is 0. So by convention, the degree of a zero polynomial is minus infinity, just for convention. So you can have a polynomial, correct? This is straightforward thing, and I'm just making it more thing. So let P a prime number. Zp is a foreign thing. Consider polynomials over Zp. Another property that is analogous to Fermat's little theorem we considered before. But before we introduce, let's consider polynomial of degree n is monic if its leading coefficient fn is equal to 1. So I'm now distinguishing a general polynomial with a monic polynomial. Monic polynomial means it's the coefficient of the largest degree is 1. Okay? That clear? Two polynomials fx and gx are equal if and only if all of its coefficients are equal. Okay? Then I can have a set of all polynomials over finite field is f of x. So now you can see, analogous to integer addition multiplication, you can define a polynomial addition and multiplication. So you can have a polynomial multiplication. So okay. So you have two polynomials. I can sum the polynomial. I can multiply the polynomial. Okay. So these are the two definitions for addition and multiplication of a polynomial. Clear?
God damn. Yes, it is.
Okay. So let's see whether there is any doubt about how do you multiply. So everybody knows about polynomial multiplication, right?
Okay, but you know, sum 2 of polynomials in fx is another polynomial in fx.
So you can you put two polynomials side by side, starting with the leftmost coefficient, and look at then you multiply the power of x, and then keep all the things. It's just basically like a classroom multiplication. Polynomial multiplication goes like a linear convolution. I mean, some of you have done the signal processing, which you will see. So the equation is given by the f of x times g of x is same as for all I, where j is equal to 0 I into fj times g of I minus j times x power I. Okay? So you take for example 1 plus x plus 2x cube times 1 plus x. First you multiply 1 with, here I'm doing, first you multiply, I'm starting the multiplication with for the second one. So 1 times 1 plus, you multiply 1 times 1, you get 1. Then you get 2x.
Oh my
Is that
god,
correct?
bro.
Can you check whether they are correct? Maybe you could,
I can't be
you
serious
get
with this
the
guy.
answer there. So you can see the last 2x to the power 4 is obtained by 2 times x cube times x, 2x to the power 4. 2x cube is 2x cube there. Then x times x is x square. X times 1 is 1. But there is also another x times 1 from the other things, which is 2x. And 1 plus 1 times 1 is 1. Okay. That's a multiplication. Okay. Now you have, so together, so what I'm saying is that set f of x together with the above two operations forms a ring, and that almost resembles like integers that we considered before. Okay?
Yeah.
Okay, so now firstly, even though a polynomial ring over ZP is of an infinite size, it has a finite characteristic equal to the characteristics of the underlying field ZP. So even though ZP of X has an infinite size, but each element multiplied by P is always 0, hence it has a finite characteristic which is P. And in fact, the polynomial rings is same as the, in fact, for the polynomial rings, characteristics of the ring is same as that of its underlying field used to generate polynomials. Now, can you prove this result? X power P to the power of P is same as A power P plus B power P, where A and B are two polynomials over ZP. See, if you take X power P, before X power P element in a field, to the power of P is same as A, see here, A power P plus B power P. So if there is only one element here, that means A power P is same as A, which is trivially true. But any two polynomials to the power of P is same as this. Yeah, you can at least, you now can you believe? Now believe it, okay? You can also prove it perfectly, but let's not get into that. I think the idea is there. So I'm now putting some of the facts. So in any f of x, subtraction is always possible, but division is not always possible, correct? So when you have a polynomial, you can subtract one polynomial from the other, because simply a subtraction means if you are subtracting one polynomial with the second one means change the sign of the second polynomial and then add it. So subtraction is always possible, but not division. So if a polynomial Rx divides another polynomial Sx, we say that Rx divides S of x, or Sx is divisible by Rx, or Rx is a factor of Sx, and so forth. But when that is the case, we write Rx times Ax is equal to Sx for some Ax. This is like, 4 times 3, 4 goes into 8, because 4 times 2 is 8. Same way, I can have a concept of a polynomial dividing a polynomial. Yeah? That's possible, right? You can have x squared dividing x to the power of 4. Yeah, that's possible. So a non-zero polynomial px that is divisible by px or alpha or by alpha, where alpha is an arbitrary field element, this is called an irreducible polynomial. If a non-zero polynomial is only divisible by itself or some or by alpha, 1. A 1 in this case, instead of some alpha, which is an arbitrary field element, then is called an irreducible polynomial. A monic irreducible polynomial is called a prime polynomial, somebody cares. Then GCD of Rx and Sx you can. So moment you have now, I can now talk about the greatest common divisor between two polynomials. And greatest common divisor between two polynomials is the monic polynomial of the greatest degree that divides both of them. So I can have a division. So if GCD of Rx and Cx is 1, then polynomials are relatively prime. And LCM of Rxm is the least common multiple of two polynomials. Rx is the monic polynomial of the smallest degree that divisible by both of them. So once you have these features, you have GCD, the division and Euclidean algorithms defined over integers will carry over to polynomial rings very easily. If you have written a program for GCD, you only change the alphabet to a polynomial ring, it will work. Instead of integers, it will work on polynomial rings also. But of course, you need to have a polynomial addition, polynomial division. So that's the kind of things. And here is an example of how a division takes place between polynomials. Okay. Here you take it. So here you see f of x is 2x to the power of 5 plus x to the power of 4 plus 3. So you see 2x to the power of 5, x to the power of 4, 4x plus 3. I'm dividing. With 3x squared. Okay? Now, when you find a coefficient here, each time quotient, you need to multiply by this quotient so that you will cancel the leading coefficient, so that the remainder now becomes less than the degree of the divisor. So here is the divisor. This is the divisor. This is the divisor 3x squared plus 1. So you can see that I want to cancel 4x cube. 3x squared goes into 4x cube. You need x. So for example, here if I put, say here is 2x x to the power of 1, here 3x squared. Yeah. So I want to cancel it. So I choose 4x cube. X cube
这个我把衣服已经晒出去了。
那谢谢，谢谢，真的。
12 modulo 5 in this case is 2, and now because of the normal division, the power of 5. So for example, here if I put, say here is 2x x to the power of 5, here 3x squared. So I want to cancel it. So I choose 4x cube. X cube is, then it becomes x5 then 3 times 4 is 12 modulo 5 in this case is 2. And now because of the normal division, we change the degree, so this will get cancelled. Then, but when you multiply by 4x cube times 3x square, you have to actually put other numbers. 4x cube times 1. So the next you try to you keep everything. X cube. I mean here you need to actually take about 4x, but I haven't taken it. But you see, then you could continue, next time you take 1, 4x cube will become x to the power of 4 here, and you start doing these operations, and finally you get the remainder. So that means you get this is the quotient times this is equal to this except for this remainder. So you can find a remainder in this way. There are many ways to do it, but this way. Let me know. Is it clear? So another difference is the nature of factorization problem over the ring. Problem of factorizing a polynomial over ZP is not hard. Unlike the problem over integers, where the problem is believed to be hard, there exists an efficient factorization algorithm for polynomials over finite field due to Berlekamp, a renowned coding theorist. After all, these rings are called man-made, basically, whereas some believe that the integers are God-made. How can you compete with a God? See, the thing is that the polynomials over finite field, it also shares similar properties with integers. But integer factorization is very hard. But for polynomial factorization, you have an algorithm, man-made, It's actually a polynomial time algorithm to factor it. So if you try to define RSA-like things for polynomials, it won't work because polynomials, they can be easily factored. So this is the thing, So initially, in the initial days when people had a thing like RSA, some people were mathematicians enthusiastic. They say, okay, I can define now with polynomial ring because it has similar thing, but it can be broken. Polynomial factorization is trivial. Not trivial, but you have an efficient algorithm. So construction of a finite fields of order, size of p power something. Now formally, it is represented by a set of all. See, I want to now construct a finite field of order p to the power of k. I have prime fields, but here is prime field to the power of k. It is formally represented as a set of all residues of polynomials in Zp of x obtained when divided by the prime polynomial of order k. So you can see that g of p power k is same as g of p x modulo px, where mx is an irreducible polynomial of degree k. Sometimes we denote this as g of star pk to denote the non-zero elements of g of pk. We'll work through the examples, okay? Here is an example I have written down as I am talking. So that way, if you read this, you will understand the idea of constructing finite field of order 8 elements. Let us see whether it makes sense. Okay? Convince yourself that 1 plus x cubed is irreducible polynomial over f2. Okay. Now is that clear? The first one? Irreducible polynomial. I'll come to you now. It can't be divisible by any other number. Okay. Divisible means, see, 1. So now I have a g of 2, right? Correct? G of 2. Finite field of order 2. What is the size of this? 0 and 1. Okay. And now I consider g of 2 of x. That means all polynomials over binary. You can polynomials of that sort 1 x, 1 plus x, 1 plus x square, 1 plus x cube, and so forth. Right? Yeah. Now the claim is that 1 plus x cube is irreducible. How do you see? That means, that means that what is the definition of irreducibility? This polynomial can be divisible by either 1, in general, alpha, which is a 1, 2, or 3 in Zp, but in this case, only non-zero element for Z2 is 1. So it will be either divided by 1 or itself. That means no polynomial whose degree less than 3 should divide it. Okay? So now this is irreducible, I'm saying. Just like this is how you see. So 5 is a prime number. 5 is a prime number. How? Because no elements less than 5 divides it. Correct? Same way as a polynomial, no polynomial whose degree is less than 2, less than or equal to 2, divide this. So let us see whether we can. So 1 divides it, because I can write 1 times 1 plus x cube is 1. Then x cube divides it, 1 plus x cube divides times 1 is 1. So the quotient, that's true. But no other polynomial, I can, for example, what are the polynomials less than equal to 2? right? What are the polynomials? The 1, 0, x, 1 plus x. Then what are the other ones? X square, 1 plus x square, 1 plus x square. 7. There is one more polynomial I left out. What is that? So the polynomial which are less than 3, strictly less than 3. One plus x square. Tell me another polynomial. Good, x plus x square. Okay. Now basically, so now you can try to divide this with all of this, 1 plus x cube here. Try to divide by 1, x. Can x divide it? Huh? No, because you see, you can cancel x cube, you can cancel up to here, but because of the 1, you can never cancel it. So x can't divide it. But that means you can divide something here, you get non-zero here. You always get remainder. So x cannot divide, 1 plus x cannot divide. One way to quickly check is that 1 plus x cube modulo d, all these divisors, is not 0. Correct? So I can take modulo, so for example, 1 plus x cube, modulo x is how much? X is 0, 1 plus x cube mod x. Mod x means is 1, because this is 0, this is 0, you get 1. So that means x, this can't divide it. Then you take 1 plus x modulo 1 plus x. Okay? So wherever 1 plus x is there, that becomes 0. Okay? So now 1 plus x is 0. That means x equal to 1. X square is equal to x. that's equal to 1. X cube is equal to x, yeah, that's equal to 1. So using this logic, you can actually find out that you do modulo all of this, you will never get 0. So that means that this is irreducible. That means you can't find a polynomial less than that divides it, and that's irreducible. In fact, there are only two polynomials of degree 3, one x. Cube and one x square x plus x cube. These are the only two polynomials that are of polynomial degree 3. So I told you about the irreducibility, right? You can always find such polynomial. Oh yeah, there is an example there. First we'll do the two simplest one, huh? Right? So convince yourself that. So you can see that now g of 8 is in the next slide. Note that the elements are computed as power of x, power j mod 1 plus x cube. Remainder is obtained by dividing by xi. Then for I greater than 1, the computation of x to the power of I is obtained by recursively multiplying x with x minus 1, correct? So in its previous entry, so also note that multiplying x is equivalent to shifting the vector x power I by 1. So also another thing that I am going to explain to you, that's pretty easy. Okay. So now I have got 1 plus x cube. I mean, let us see all the polynomials after dividing by x cube. What are the things you can get? Let's say I have 1 plus x plus, and let's see all the polynomial, but I take all the g of 2 of x modulo. I do all this over this. Okay? Just like I say z modulo 9, 2, right? Or z modulo 7, for example. All the numbers that z modulo 7 I get is 1, 2, 3 up to 6. 7 is 0, so 0. Okay? Same way here, I do with polynomials. So I have whatever may be the polynomials. Whatever may be the polynomials, but at the end, what will be the remainders? Remainders will be either 0, okay, or x, or 1 plus x, or x square, 1 plus x square, x plus x square, and what else? Another one. Two more. One itself, 1 plus x plus. Right? So and you can see that they actually corresponds to all possible binary numbers. Degree 1, x, this is x. So let's say we'll put it x here. Then x square is this. So I'm sorry, I'll start with another. So here we'll have 0 is 0, 0, 0. 1 will be, I don't know, let me check how I have, because it's also important. So let's take 1, 0, 0. That means this is the power of x0, x square. Okay? So any polynomial has to be sum of these, right? I can represent this as this 1. X is this. X square is this. Sorry, x is there, and then x square is there. Okay. Right? Then x cube. What is x cube? Very good. So now 1, 1, 0. Because 1 plus x. Because x cube well, 1 plus x cube is 0. Basically, I can take the x cube to the other side. 1 plus x equal to x cube, correct? Because when I take modulo 1 plus x cube, 1 plus x is 0. X cube is 1 plus x. So when I have x cube is 1 plus x, what is x to the power of 4? I have to just multiply by this, right? So multiplication of this number, 1 plus x by x, is simply shifting this number. Because this is 1 plus x, so this is 0, 1, x, x square, this is 1 plus x. This will be x plus x square, correct? So that is shifting, and x to the power of 5 now, which is basically it will be shifting by another thing. So which will be, what is x power 5? Let's compute here a little bit. X power 5 is x square plus x cube, correct? But x cube is 1 plus x. So x square plus 1 plus x, which is same as 1 plus x plus x square. Now x to the power of 6 is how much? X power 6 is, now you take x power 6, you got this 1 plus x square times x, which will become x plus x square plus x cube. Now x cube we can replace it by 1 plus x. 1 plus x, now you do x plus x square, but x plus x cancels 0 and you get 1 plus x square. Okay. Now let us say what is x power 7? Multiply by one more time. What happens? So now x power 7 is 1 plus x square times x, which is x square, x plus x cube. But x cube is given by x plus x cube is 1 plus x. X cancels, I get back 1. So now you see I got back to this one. I started with 1 and then I go to x square. So all non-zero elements under multiplication of x. Now such polynomials for which you get all possible polynomials by multiplying x, they are also called as primitive elements. Primitive prime polynomials. But this x is a primitive element because it now generates the entire group. Just as when I take z as z7 as z11, I say the 2 is a primitive element because 2 divides all modulo 11. Same way you got all elements here. This is the idea. That is. So if you have understood this, then you have understood general representation of finite fields. So now let's say, now your question, you wanted why I should do it with other than 2. So here you can convince a finite field with 9 elements. Now in this case, 2 plus 2x plus x square is irreducible polynomial over F3. You can convince in doing the same thing. You can't find an element polynomials whose degree less than or equal to 1 dividing this polynomial. This is given to you, assume. Okay. Now I'm going to construct a polynomial g of 3 square. G of 3 square means how much? 3 square? 9. So that you construct a finite field of 9 elements. So leaving 0, you get
I won't lie, this one's pretty hard to understand. I will read what it says here. And I think after I read this will be the last thing I do, because I've done quite a bit of study, you know. We're talking, how long has this stream been going for? Yeah, 3 hours and 12 minutes. Do some more in the afternoon, but let's read this finally. Last thing before I take a shower and do other stuff. Convince yourselves 1 plus x plus x3 is an irreducible polynomial over f2. Now f2
of x0 is x square. So any polynomial has to be sum of these, right? I can represent this as 1, x is this, x square is this, sorry, x is there, and then x square is there, okay, I'll put that. Then x cube, what is x cube? Very good. So now 110, because 1 plus x, because x cube, 1 plus x cube is 0. Basically, I can take the x cube to the other side. 1 plus x equal to x cube, correct? Because when I take modulo 1 plus x cube, 1 plus x is 0. X cube is 1 plus x. So when I have x cube is 1 plus x, what is x to the power of 4? I have to just multiply by this, right?
Are you taking the XOR? If it's the same, it should be 1. Oh, it's like the negative XOR or something.
So multiplication of this number 1 plus x by x is simply shifting this number, because this is 1 plus x, so this is 0, 1, x square, this is 1 plus x, this will be x plus x square, correct? So that is shifting, and x to the power of 5 now, which is basically it will be shifting by another thing, so which will be, what is x power 5? Let's compute here a little bit. X power 5 is x square plus x cube, correct? But x cube is 1 plus x, so x square plus 1 plus x, which is same as 1 plus x plus x square. Now x to the power of 6 is how much? X power 6 is, now you take x power 6, you got this 1 plus x square times x, which will become x plus x square plus x cube. Now x cube we can replace it by 1 plus x, 1 plus x, now you do x plus x square, but x plus x cancels 0 and you get 1 plus x square, become 1. Okay. Now let us say what is x power 7, multiply by 1 more time, what happens? So now x power 7 is 1 plus x square times x, which is x square, x plus x cube. But x cube is given by x plus x cube is 1 plus x. X cancels, I get back 1. So now you see I got back to this one. I started with 1, and then I go to x square. So all non-zero elements.
Holy moly, man. Like,
under
this is
multiplication of
fucked,
x.
but I get
Now
it.
such polynomials for which you get all possible polynomials by multiplying x, they are also called as primitive elements. Primitive prime polynomials, but this x is a primitive element.
Okay, so now it's time for me to have a shower. Alright. We're calling it a day, guys. Goodbye. I'm gonna do some, take a break, and then, there's interviews that I gotta do later. Alright, bye, guys. Bye.